Hello everyone. So today I'm going to talk about the shortest distance algorithms. Different algorithms available for shortest distance. Shortest distance algorithms. Now, basically, when we talk about shortest distance, two main approaches come into the picture. Okay, one is BFS, because what we do in BFS, if you remember, we do level order traversals. Okay, we go level by level and we go to all children of a single parent, and then we move on further deep. We can't use DFS much for the shortest distance, because for DFS what we do, we go into as deep level as possible. Okay, now this couldn't be the shortest path. Now this could be shortest path, that this is level 1, so it could be distance 0, this is distance 2, and then this is distance 3, something like that. Okay, so we'll always go for BFS. And the other is Dijkstra's algorithm. Dijkstra's algorithm. Now, I didn't go much deeper into the Dijkstra's algorithm because there are a lot many questions on Dijkstra's, which is DP plus Dijkstra, mm, Toposort plus Dijkstra. It could be DSU plus Dijkstra. Okay, so I'll not go much into the Dijkstra. I'll just discuss it from the top on very uber level. But I wanted to go to BFS today. And first of all, I wanted to make you understand the difference between these two. Now, when to use BFS? BFS will use queue and the Dijkstra will use priority queue. Okay, and we will use minimum priority queue. Okay, this will use queue and this will use priority queue. And that too will use minimum priority queue. Now, why queue? BFS of course uses queue. So when this approach work for BFS, when we have same weight nodes, same weight edges, sorry. Okay, all edges should have same weight, then only this approach will work of BFS. And when the edge extra will work, it will work for varying edge weights. Okay, when your weights are varying, this approach will work, the edge extras algorithm will work. So this will work for same weight edges, this will work for the varying edge weights. Cool. Now, for the same weight edges, what you'll see now, what you'll store in your queue. So, of course, you will store what? A source node, that is a node, and its distance from source. This distance will be from source, and this is your node. Okay, current node. And this distance is from source. Same way we will store in the priority queue also. But priority queue will just take care that while it stores in the queue, it will take minimum on top. That is, if you have edge varying weights also, then also minimum weight or will come on the top. So minimum distance weights nodes will be on the top. While this it has all the same weight, so it doesn't creates any difference. Okay, now let's understand this by example. Now let's say you have a single weight nodes. Okay, so your 1, 2, 3, 4, 5, 6. Now from this node, from a single node 1, you need to find the weight of all other nodes. Okay, it could be all other nodes, it could be a single node to single destination node. Anything will be worked by BFS. Okay, single node to single destination, DFS will also work, but we will prioritize BFS as that was the efficient approach. This was the efficient approach in that. Now let's say you need to find the distance from 1. So you are given the source node and assume you have to find the distance of all other nodes. Okay, so what we will do, we'll create one distance array, of course, of size 6 because we have 6 nodes. Okay, we'll put it 7 because my nodes start from 1. Okay, so your source node will be 1 over here, let's say. Okay, and you have to find the distance of all other nodes. So first step, make distance of all nodes as maximum, as int maximum, or 1e9. Make it 1e9. Okay, that means currently you're putting all distances 1e9. Second, distance of source should be 0 because from source to source is 0. This distance will be your destination. Like if your I is destination, then distance from source to I will be stored in distance of I. Okay. So your distance of source is 0 and you will push what? Your source and its distance, which is 0, in the queue. Now third step. While not queue.empty. Now let me write it in the algorithm form over here only. So while not queue.empty, what you will do, of course, you will take a queue's value, that is q.front, q.pop. Now we know this node is the parent of all the adjacencies nodes. So what we'll do? We'll go to all its child for auto ampersand it in adjacency of this node. Okay, this could be child. Let it be child. What you'll do? What you'll check? What you'll check? If the current distance of this child is greater than this node's distance plus the weight. Assume the plus weight is x. Okay, same edge weights as x. All edges have same weight of, let's say, x, 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 x. Okay, so what will be your newer weight for this child? So if distance of child, that is the current distance, if the current distance whichever you have calculated, if not calculated, it will be 1e9. Very good. So if distance of child is greater than your x, which is the edge weight, plus the distance until the parent node, which is the node, if this is possible, that means your child is still more. If I put this new weight, then what you have to do? You have to put the new weight. So you will do distance of child as your new weight, which is x plus distance of node. And you will push what? This child node and its distance in the queue. So next time, its child will also be uh, get into the picture. Now, if you have a single node to find, let's say you are given the destination, okay, your destination node is, let's say, dest, okay, then what you'll check, if your node is equal to a destination over here, then you will return this, you will return distance of this node. Okay, no need to move further. But if not, every time you have to go, and when you are coming to this node point, you will update. Anyways, your distance array is getting updated with the new values. So your distance array, final distance array, will contain all the distance from source to all the nodes, and this will an array, this will be an array. I hope you're clear. This is the simple BFS approach. Remember, if you have same weight from one node to another node, or from one node to any node, or from one node to all nodes, you will use this BFS approach for sure. Clear? I hope you're clear with this. Okay, let's solve one problem on this then. Okay, one important observation for the BFS approach. Okay, one important note is this: whenever, okay, mark my words clearly, whenever you visit any node for the first time, whenever you visit any node for the first time, that time itself you will get its minimum distance. That time itself you will get its minimum distance. Now, why am I saying this? Because we assume that all the nodes have same edges, okay? Same weights for all the edges. Now, let's say you have 1, 2, 3, 4, 5, 6. Cool. Now, let's say this all weights are 1. Now, from 1 to 2, I'm putting the weights with the blue color. Okay, 1 to 2 is the 1 distance. And then 2 to 3, so 1 to 3 will be 2. 1 to 4 will be 1, of course. 1 to 3. So this way it came to, okay. So let's say for what, okay, my bad. Remove this. Okay. BFS approach, what you'll do? You'll go from 1 to 2 and 4. So this distances will be 1. Then with 2, you'll go to 3 only. So this will be 2. And with the 4, you'll go to 3. So again, this will also be 2. So 3 will be 2 only. Okay. 3 has 2 distance. Now with 3, you can go to 5 and you can go to 6. So this will be 3, 3. Now with the 5, you can go to 6, but then that will be 4, which is anyways longer than 3. So first time weight is minimum. Here also, with 1 you reached 4. With 3 you can go to 4. Okay, but first time you reached 4 via 1, and that is the only minimum distance. So whichever your node you visit for the first time, okay, you visit any node for the first time, that time itself you will get its minimum distance. So if at all you will not compare this thing, okay, if you'll ignore this if part, and what you'll do instead, if you just put if distance of child is not equal to, sorry, equal to 1e9 or int max, whatever you have put, that means you have never visited. So this distance will in itself work as the visited, or you can put the visited also instead of distance. I hope I'm clear. So let's solve a 2D based question out of this, a 2D graph based question, and there we will use visited now instead of distance, and that will also work. Cool. Okay, so fine. So you're given an n cross n binary matrix grid. You have to return the length of shortest clear path in the matrix. If there is no clear path, return -1. Clear path is a path from the top left cell, that is from 0, 0, to the bottom right cell, that is the n-1, such that all the visited cells of the path are 0. You can visit on the cells which are 0 only. Okay, you cannot visit on 1 cells. Okay, plus all the adjacent cells of the path are 8 directionally connected, that is you can go in 8 directions. The length of the clear path is the number of visited cells in the path, number of visited cells in this path. So here it will be 2, here it will be 4. Okay, so here you have to put from source to source is also 1 distance and not 0. Okay, because it said number of visited cells, it will consider the source also. Okay, first, what approach you will follow is you will make an directions array. Okay, so we have one vector of pair of int comma int, which is directions -1 0 -1 -1 -1 1 0 -1 0 0. Oh, sorry, you have to go to the 8 directions. You can go on top, on left, on right. Okay, not 0 0. Okay, 0 1, and then 1 -1 1 0. Done. Okay. We'll have one bull is safe. That will pass int I, int j, vector of int ampersand grid, and we will do this with visited. So I have one visited array also, which is anyways 2D grid. If at all you make it distance, then also it will be 2D. You'll initialize it with 1e9. But I wanted to make sure, okay, that this is for sure for the BFS because all have same edge weights. First time you visit, that will be the minimum only. Okay, so visited. N is equal to grid dot size. Now it should not be visited and it should be 0. So return I greater than equal to 0 and I less than n, and then j greater than equal to 0 and j less than n, and not visited I j, and grid I j is equal to 0. This will return true, also it will return false. Okay, now you have n as grid dot size. Make, of course, a visited array of n cross n. Cool. Now You start traversing. And if there is no clear path, we have to return minus 1. Okay, fine. So now you have one q. Q of what? You need to store three things over here. So let me just store vector only. Okay. First will be my ith, row number, column number, and the distance. So what I'll do is I'll push q dot push 0 0 and its distance as 1. Why 1? Because we have to consider that source as I have explained. Okay, and we will do visited of 0 0 as also 1. Okay. Now while not q dot empty, int I is equal to q dot front 0, int j is equal to q dot front 1, and int distance is equal to q dot front 2. Clear? Pop it out. Now go to all other nodes. So for auto ampersand, no, okay. So here you have to go in four directions. So for int, let's say, or I can go for auto ampersand element in directions. Okay. Int new I is what? This is your old I plus element dot first, and int new j is j plus element dot second. Okay, distance is 1 only as it was said. Okay, now if is safe, what? This new I, new j, grid, visited. Those four things. If is safe, then you will mark it as visited, and you will go to that path. So what you will do is you will mark, okay, here we have to just go to a particular destination. So I can make my answer array over here. Int answer is equal to 1. By 1, initial distance is 1. Okay. And if you have got, so if I is equal to n minus 1 and j is equal to n minus 1, we will return distance from here. We will return distance from, okay, I don't need answer. Sorry, my bad. Okay, we'll just check it over here. So if visited ni and nj is 0, and its distance will be what? That distance plus 1. So I'll push in q what? This new I, this new j, and distance plus 1, of course. Okay, and we are done. We don't need this answer. Okay, if we haven't got anything out of this while loop fully completed, that means we never reached that last cell, so we'll return minus 1 over there. The first, okay, first row and column should also be equal to 0, then only it will work. So if grid 0 0 is equal to is not equal to 0, that means your first starting row is only not 0, you will return 0 out of there. Or your grid n minus 1 is equal to 1. Okay, in that case you will return minus 1 in itself from here. Cool. Okay. Nijikshtra, I'll make a separate playlist out there and we'll understand that. Okay, I'll put some questions here, and there is one question of shortest path for DAG, directed acyclic graph. You are given directed graph only, but it was not cyclic. Okay, how will you find the shortest distance out of there? So what you'll do for the acyclic graph, that is no cycles and directed, you can of course find the topo sorts. So you will find the topo sort node, okay, in which order you have to visit the nodes, and then in the topo sort order you have to start traversing. Okay, so that your first node should be the source node, and then you'll find the distance out there, and that way you'll get the shortest distance of all the nodes. So I'll put that link also below if I'll find. Here we complete our shortest distance. I'll find some questions and put it in the description. Please to solve that, and uh, maybe I'll create some miscellaneous questions in the next video, and if not, I can move to topo sort list or the